Hello, guys. Welcome to my talk, Monadic Parser Combinators with Scala 3. I know it's sort of a tongue twister, but you'll see soon that it's not as complicated as may sound. Um, okay, so I like hands-on tutorials, so we are going to build today something that is sort of fun, I guess. We're going to build a very simple parser for arithmetic expressions, something that any calculator will do. For example, we have very common operators, for example, like sum and division. As you can see, it preserves order of operations, so that's something that we'll explore how to do it. We also have a couple of built-in functions like the square root of a number, and we also have those functions receiving expressions in sort of a recursive way. So that's sort of interesting for a parser to have. Okay, so I've just realized that you are not seeing the changes in my screen. Okay, so now you should see it. This is the parser we are going to build. It has a couple of arithmetic expressions down here, and that's it. So first of all, why should you care at all? So DSLs. Maybe your company might want a custom language to express common patterns and configurations for certain kinds of services. I've done this in the past. They enable very expressive languages for tailored, suited use cases, and they are very effective, in my opinion. So in this book, I read Effective Haskell, where Rebecca Skinner created a chapter-long example of how to deserialize heterogeneous data using Haskell and Monadic Parser Combinators. That it helped me actually see their value in common engineering problems beyond examples like the small calculator we are building today. I arrived at this topic because of a book by Graham Hutton, Programming in Haskell, and I just simply couldn't believe my eyes at the beginning because they looked like kind of the magic we don't like as programmers because they hide too much details of how they work. But that's far from the truth. They use very common and simple patterns borrowed from category theory, like those kind of abstractions that were never intended for a kind of use, but nevertheless they just fit. They are astonishingly elegant, clean and elegant. So a couple of facts about me. My name is Bryan Garzon. I'm working for Seaverge as a contractor. I don't have decades of experience like the rest of speakers. This is actually my first talk. I like Russian novels and military campaigns. I'm not as smart as the rest of speakers, but I'd say that's a good thing because it cost me a bit wrapping my head around these concepts because at the time I was learning to program with categories. So I really appreciated the bit-by-bit nature of Hutton's writing in his programming Haskell. So I want to build on that legacy and teach easily some Scala programmers one more cool thing they can do with monads. So first of all, what is a parser? So we can see a parser as just a simple function from a string of characters to some result. This result, for example, may be a float, but actually the result of a parser might be something else, maybe something that represents a token or a syntax tree. So we are going to have this output parameterized. The output might not be exhausted at the end of the parsing, so we are going to also return that sort of unparsed element in each result of our parse, and so other parsers can pick up from there and parse the rest. And also we have to take into account that the parser might fail, so we are returning this just instead of just a tuple, we are returning an option. Okay, so I'll have this very simple extension method, which is just a method that just calls the parser. Sorry, my cats are doing a mess. Okay, that's it. Uh, so we're going to have this extension method for just to make clear when we are building a parser or actually calling the parser to do the real thing. So for example, in this case, these two expressions are exactly equivalent because our parser, remember, is a function, but the one on the right is just clearer. So that's why I did it. This is what we are going to see today, so stay tuned. Okay, so first of all, we are going to start by explaining two basic and some parsers that are going to serve as bases for the rest of the parsers we are going to build. And this is the empty parser and the item parser. The empty parser is just a parser that ignores its inputs and just returns nothing nothing. That's hence the name empty. For example, if we parse the empty parser with an ABC, well, then we'll just have a none as a result. The item parser instead, what it does is just takes the first character of the string we are going to get as input, and that's the parsed thing, part of our result, and the tail is the unparsed part of the result. So for example, if we use this parser with ABC, then we are going to have a tuple with A being the parsed part of the result and BC being what's left. So why even bother with monads? Because as you can see, parsers are just a function. So we can actually use these constructs without monads and don't complicate our lives. But we're going to show an example of what monads will save us from. So I'm going to showcase a simple parser, the parser ensure. Sure is one of the most basic parsers. It takes a character and ensure it satisfies a predicament. So for example, if we have a parser ensure that ensures the first character it gets is a digit, if we parse it with an input of 1BC, then we are going to get a successful result with 1 being the thing we have just parsed and BC being what's left. If we use the same parser with, for example, ABC, then we are going to get a none as a result, an error. This is how it looks without monadic behavior. As you can see, for building this parser, we first have to use it to actually invoke the parser. We have to pattern match each of the possible results. In this case, for example, none. We propagate the none because we can't do anything with it. But if we get a sum, then we do something on that parsed value. We check if, for example, it satisfies the predicament, and we wrap again the result so the parser can continue and doing nothing if we get a sum that doesn't satisfy the predicament. So now I want you to imagine what this means for more complex parsers, because this is one of the most simplest parsers, and we already have a very cumbersome and sort of just ugly implementation that we are going to have to repeat and repeat for basically every single parser we want to build. So I want you to look at what with monadic behaviors the ensure parser will look like. It's just a for comprehension where we use the first class syntactic sugar of Scala to take the value from the parser do something with it. By this time, it's just check the predicament and then return a value. So as you can see, we got rid of matching and propagating errors. We only care about the successful results and how to use them, and we use the first class syntactic sugar. So can you spot the pattern? The pattern is quite simple. We use a value wrapped in a context. We do some operation over it, possibly returning another context, like wrapping that value in another context, and then we will have to return the new value still wrapped in that context while propagating errors ourselves. But that's all categories are about. That's why categories exist. They are basically represent sort of functions between objects inside sort of a nebula or of something, a context. So we're going to first start by implementing a functor for a parser. So what if we want to transform what's inside the parser? Um, so this transformation is commonly put under a name called fmap. Fmap is a function that takes a parser, takes a function that goes from what's inside the parser to another thing, it may be the same type, and returns to us another parser. So for this implementation, it's quite simple. We just take our input, we just use it in our parser, propagate the none as a result, and then if we get a sum as the result of the parser, we can use that function on the parse part of the result, and then we will have this new parser of type B. So this is cumbersome to pass, especially in Scala, to pass our parser as a first parameter. So we are going to build to create a new extension method, which is a syntax extension method for Scala 3, which is just syntactic sugar for receiving something as the first parameter. So in this time, we are just going to invoke the fmap function we already did. So you can see the item parser we did earlier. If we, for example, map what's inside the item parser, which we already don't know what it is, to an uppercase letter, and then we, for example, invoke that parser, which is it's not a result, but a description of how to get a result. If we use it with the input ABC, we are going to get the tuple A, the character A as the parsed part, and BC as the unparsed. So for applicative, we are going to need our parser to have a function from the applicative category called pure. This is kind of cool to think about when you make your head around that parsing is an effect. But if, for example, in this case, we are sort of putting the input just as an unparsed part of the input and putting the value of pure as, sorry, it's my cat messing around. And if we put the value as the parse part, then it makes sense we call this pure because it's not doing anything. It's just putting the whole input as unparsed. Wait a second. Okay, here we go. So normally applicative has another function called apply app, but we are not going to need it today, so I'm going to skip it right away. As an example, if we, for example, put the char 1 and parse 2, 3, 4, we just get as a result the one we put into as pure and the 2, 3, 4 as unparsed. So we did non-parsing basically. So now we have to flat two parsers. What I mean by flat? By flat, I mean that we have our parser of type, for example, A, and then we have a function that not only returns another type B, but returns another parser of type B. And instead of getting a parser of B, we want to just get a parser of B. So the implementation is quite simple. We call the parser on our input of B, which is the parser we are building. We propagate errors, and if we get a successful result, in this case the sum tuple parsed and unparsed, then we can call the parsed part with the function we are receiving, and then that's going to give us a parser, and we want to call again that parser with the unparsed part we got. So it sort of flattens both parsers and make them just one parser. Again, we are going to use an extension method. We are going to create two extension methods actually. Once is called flatMap, which is the commonly used name in Scala for bind, which is going to just call bind, and that's it. And we are going to have this sort of infix operator, which just looks nice, and that's why I included it there. So as an example of how bind or flatman works, for example, let's say we have a reject if digit one function that takes a character and gives us back a parser. Because why give us back a parser? Because we want to represent an empty result, sort of a rejection of what we received as a digit. So for example, if we want to reject one, then we are going to return empty as a empty, and otherwise we are going to return the digit just as we as it was invoked with. If we create a parser that first ensure that the first character is a digit and then reject it all away if the digit is one, then we, for example, we can use it by parsing, for example, A, which it sort of fails fast and doesn't even get to our reject digit if digit one. So it gives us a none right away. If the character is a digit, but it's a one digit character, so we are also rejecting that one from this function. But if the character is a digit and also is a digit that is not one, then we are getting an actual result. So for enable for comprehension, the Scala requires us for us to implement something a inline method called withFilter, which is a class that sort of receives the parser and the predicate to filter over three common operations: map, flatMap, and withFilter, which is sort of a recursive call to withFilter. I'm going to skip on this implementation because it is actually not important. You can check this Scala documentation out. This is what enables using for comprehensions for any arbitrary type. So we have ensure again. So we have already shown you the definition of ensure, which is this very clean for comprehension like structure where we just filter X if it satisfies the predicate and we return it and yield it right away. So with this ensure parser, we can construct a family of parsers. For example, the char parser, which ensure that the first character we are consuming is a given character. So for example, X, if they are both the same. So for example, if we parse X, a char X, and we parse it with X, Y, Z, then we get a successful result having x as the first parsed part. And if we don't, and then this parser fails. Another other parsers we can build from there are the digit parser, which ensures a digit, lower ensures is a lower, and upper ensures is an upper. Quite simple. So now we need the ability to try multiple parsers, because as I mentioned, that's a very key component of the kind of parsers we are building. So for example, uh, for example, a letter might be a parser built by a lowercase letter or an uppercase letter. To do that, we have to build a method called combine k, which simply uses the first parser. If we get none, then we use the second parser, and if we get a result, then we use that result. We use an extension method just to make it nice to use it, like right here. So yeah, it is just cleaner to use. And we can define another alphanumeric parser, which parses a letter or a digit. So the string parser is a parser that we want to create for matching an exact string. For matching an exact string. For example, if we pass the string const and we pass an expression, it's something like resembling a JavaScript expression, then we have a result of const in the unparsed part. But if we got something other than const, then it will fail by comparing even the first character, and it will yield a none. The implementation is quite simple. It receives the string, it checks if it's blank, and as a base case for a recursion, it takes the head, it takes the tail, and it with the char parser we've just done, it checks if it satisfies it is that x, and then it calls recursively this function. So now we are going to implement repetition. And this one is quite cool because it can be represented by a very nice mutual recursion algorithm. So what we are going to what we want with this parser is, for example, if we want many digits, this will consume as many digits as it can, but it won't fail if it doesn't find any digits. So it's sort of like it doesn't fail. It cannot fail. It always be returning a list at least. But some is like a many one. Because it fails, it doesn't find at least one of the parsers that it is supposed to find. So the implementation of these are very, very simple. They are just a mutual recursion, because some is like many, but with a fallback of an empty list, right? Sorry, many is like some, but with a fallback. Some is like many, but consuming the first, at least one of the first parsers, so, and then calling many. And many is some, and some is many. So that's a cool algorithm I wanted to emphasize. So now we have many and some. We, for example, can ensure white spaces and then just parse as many as possible, even if they are zero. And then we discard the result by using map and using a unit. We can also parse integer literals so for example, parsing some digits, that means at least one, that's a natural number. An integer number is it receives at least a char of minus sign, and that negates the result of the natural number, or is just a natural number. And a decimal is an impart with a point char in the middle of some digits at the end of the decimal, or it is just a natural number. So tokens and symbols are parsers that are surrounded by white space. So for example, we have white space surrounding this parser, and we return the parsed thing. And symbol is just the string parser, but sort of tokenized. That means it can be surrounded by white spaces. So with that, we can build natural and float numbers. And now we are going to see how the arithmetic parser works. First, we have our grammar, which is an expression can be a sum of expressions, a multiplication of expressions, an expression of between parentheses, or a function application of an expression, or a natural number or decimal number. We can do something called sort of create a level for each level of application, and this will give us sort of the precedence of operations we want. We can also do the recursion only on the right side, because sum and multiplication are right recursive. So for building an expression, we have left the term on our left. We have our symbol on our right. It can be a plus or a minus. We can have our expression after that, and we have the option, sort of this optional structure of sum, sub, or maybe just the term we have just consumed. For term is basically the same, but with one level above, so it has higher priority. So it is a factor with a symbol, with a term, and the optional of those numbers. And then we have parenthesized expressions with they are built by sort of the symbol of opening and closing symbols, and then the expressions inside them. And then we are going to use them to maybe just return them or apply a function to them. And that gives us the sort of the optionality of having parenthesized, the square root, the power, or the decimal parsers. For modeling errors, I just did a couple of case classes for when input was invalid or it was unused. And then for evaluating an expression is just using the expression parser and use the parse method for parsing the input. And pretty much that's it.